Hi, welcome to the isotope lecture. We are also going to talk about fusion and fission. So let's first define what is an isotope. It's an element with a different number of neutrons. So I know we talked before about hydrogen, for instance, or rather about all elements having the same number of protons as they do electrons. When we talk about isotopes, we're only talking about protons and neutrons. So let's look at the example of hydrogen right here. You could have a hydrogen atom with 0 neutrons and 1 proton. You could have a hydrogen atom with 1 proton and 1 neutron, or you could even have a hydrogen atom with 1 proton and 2 neutrons. I know, right? It's mind-blowing. A lot of our elements have multiple isotopes. We find that there's usually one isotope that is most common. And so when we talk about hydrogen or helium, we talk about its most common isotope and not all of the options that we have. So again, most atoms are going to have the same number of protons and neutrons. I know we talked about that in an earlier presentation. But some are going to have fewer neutrons than they have protons. And some are going to have a variety of numbers of neutrons, as we have in these examples right here. When we figure out the atomic mass number, which is also called an AMU, the atomic mass unit, when we see it has a decimal point, that tells us we have an element that has more than one isotope. And if you look at the atomic mass number, the atomic mass weight, you're going to see that most of those have decimal points. However, if that decimal point is really, really close to a whole number, like let's say it was 8.03, that would tell us we don't have very many varieties of isotopes, and also most of them are the sort of main standard where we have an equal number of neutrons and protons. All right, so that's atomic weights. That's how we determine that, is by the number of protons and neutrons present in all of the isotopes. Fusion is where we have 2 or more nuclei joining together. When we have fusion, when we have 2 atoms coming together, there's an amount of energy that is released by their fusion. And it's only going to happen with light elements. Heavy elements will actually break apart to release their energy. Now, we talked just now about hydrogen and helium. Those are 2 that we frequently see going through that process of fusion. And in fact, hydrogens fusing to form helium atoms are what have generated all the energy at the core of the sun, which, by the way, is where all of the energy on our planet comes from. Sunlight is converted by plants into energy that all of the other living things on this planet rely on. So it's a pretty major big deal to have that fusion happening at the sun, and we also see it happening in other things. For instance, the hydrogen bomb releases its energy because of the hydrogen fusing to form helium. And when that fusion happens, we have a huge amount of energy released in a controlled manner, hopefully controlled manner. And this is what that looks like. We have one isotope of hydrogen with another isotope of hydrogen. When they fuse together, there is a leftover neutron and it gets kicked off, and this is what can create and generate a lot of energy. And the product of that fusion is this helium molecule, which has 2 neutrons and 2 protons, which makes it a very stable helium molecule. This is the one, the neutron over here, that's floating around now looking for some place to land, is what generates all that energy. Now, fission is the exact opposite. Instead of forming a new molecule from light molecules, we end up forming 2 molecules from one heavier molecule. So it's the breaking apart of a heavier molecule into 2 lighter molecules, is how radiation is generated. Now, in general, the product, the 2 things that come out of this fission process, are equal to half the original mass, but usually there are 2 or 3 neutrons also released in this fission process. And remember, as with fusion, those little floating around free neutrons are what cause a whole lot of energy to be released. So it's another way to also generate energy. This fission or fusion process that releases neutrons can also trigger a chain reaction. that looks like this, where you have one little neutron all by itself as a product of either fusion or fission, and it bumps into, as it's floating around or moving around, it bumps into another nucleus, and the energy from that bump can end up splitting that other product, this nucleus right here, so that again we have two equal parts and some leftover neutrons. So I want you to picture a whole bunch of this material and all these neutrons bumping into it and splitting it apart. Now this can only happen, or generally happens, in radioactive material, not stable. If it's stable, when that neutron bumps into it, it just sort of repels it and moves on to another area. All right, we have two heavy elements that are primarily used by humans for radiation. There are other things that are radioactive that are not as useful for humans in the creation of thermonuclear weapons or energy. So uranium is the most common one that we use. 238 is very stable. 235 is fairly unstable. Now, in just a minute, we're going to look at the rules of what helps you determine whether something is stable or not stable. 235 is unstable. There is a lot more 238 in the world than there is 235. A very small percentage of the uranium occurring naturally is 235. So there has to be a process, and there is a process, for separating out those two isotopes, which look very much alike to the naked eye. So it has to be a microscopic chemical process that identifies those and sorts them out. Another element that we use for nuclear power and nuclear weapons is plutonium. Plutonium-39 is our unstable version. Please notice that uranium-235 and plutonium-239, those are odd numbers, 235 and 239. That's one of our things that determines whether something is unstable or stable. 239 doesn't occur naturally at all in the environment. You can't mine plutonium-239 anywhere. It has to be created in the lab. And Hanford, Washington, which is along the Columbia River, is actually one place where plutonium-239 has been created. All right, so let's check it out and figure out what makes something stable or unstable. So a stable isotope is determined by the number of neutrons to protons. If it's an even number, so if the number of neutrons can be evenly divided by the protons, we're going to have very stable. If it's unstable, this is the type of isotope that is radioactive. So anything with an atomic number less or equal to 20 with a neutron to proton ratio of about 1 is going to be stable. So for instance, if it's atomic element number 19 and the number of protons it has, we already know is going to be 19. And let's say that the number of neutrons is 18 or 20, that's pretty close to 1. That's going to be a stable element. But if we had atomic number 19 with 19 protons and 40 neutrons, that's actually slightly more than 2, and that's going to be an unstable element. Elements with an atomic number greater than 82 generally are unstable or have multiple isotopes and have a higher number of unstable isotopes. Anything that has an even number of protons and an even number of neutrons, any of those isotopes tend to be stable. So when we looked at plutonium and uranium, uranium-238 is stable. It's got an even number of protons. Anything with odd numbers of protons and odd numbers of neutrons tends to be unstable. So let's look at an example. Here we have 3 different isotopes of carbon. We have carbon-12 with 6 protons and 12 neutrons. We have carbon-13 with 6 protons and 13 neutrons. And we have carbon-14 with 6 protons and 14 neutrons. So if we think back to our rules of stability, if we have an even number of protons to neutrons, we tend to have a more stable element. So automatically we know that carbon-13 is less stable than carbon-12 or carbon-14. To figure out which of these is more stable, carbon-14 or carbon-12, we then have to look at how do the protons divide into the neutrons. So if we divide 12 by 6, we end up with 2. So that's a straight up even number. If we divide 14 by 6, we end up with slightly more than 2. We end up with 2.3. So that shows us that carbon-14 is less stable than carbon-12. So go ahead right now and write down the order of stability between carbon 12, carbon 13, and carbon 14. You record which of those is more stable. If you need to rewind, go right ahead. So the next thing we can talk about is half-life. And this is the radioactive model that you did earlier, showing off, or maybe you haven't done it yet, showing off how the decay of radioactive material occurs, the rate at which it occurs. A half-life describes the time it takes for 1/2 of a sample of a radioisotope to decay. So how long does it take for carbon 14 to become nitrogen 14, or rather half of the material that you have that's carbon 14 to become nitrogen 14? Now this is very predictable, and we can actually use this to date samples of material that have carbon 14, which is pretty much anything that's living. And we use it, it's a very slow half-life, so we have to use it for things that are very, very old. For instance, we can't date anything that is less than 5,000 years. That's the half-life of C14, because it won't have decayed enough for us to have an accurate measure. We can use, well, we actually can't use uranium-238 to date anything because its half-life is the same as the age of our planet. Uranium-235, on the other hand, is a mere 704 million years, so it can be used to date things, although C14 is used more frequently, or carbon-14. All right, so if you need to rewind, feel free to do that. Otherwise, move on to your next assignment. Good luck.